Hello there. Today we will see clambers. Actually, this is a revision video. We have finished studying clambers, but I'll just go through one type of clamber, positive clamber, and one type of negative clamber in case you have any doubts later on. We saw many types of clambers. We saw positive clambers, we saw negative clambers. Then there was biased and non-biased, meaning you might be adding a or you might be applying an extra bias or not. Then you might be using ideal diode or practical diode. So based on these specifications, you might have different types of clambers. The one that we will discuss today, that I will discuss today with you, is positive biased clamber using practical diode. It covers almost all the cases in here. That's why I've chosen this one. Let's see positive biased clamber with practical diode. How do you understand the working? Basically, positive clamber means it will clamp the waveform in the positive direction. As you can see, the arrow direction is upwards, meaning it is clamping or pushing up the waveform in the positive direction. Okay, that's how you can remember the direction of the diode here in clamper. Let's start. This is your basic circuit. You start with the circuit always, and the first case that you will always consider is when is the diode forward biased. The diode is forward biased when the voltage at this point N, Vn, is less than the voltage at this point. Because this is N and this is P, the voltage at N should be less than voltage at P. In order to ensure or in order to understand when this happens, I have to draw the equivalent circuit of the circuit. So I draw the equivalent circuit. Of course, V in this voltage is applied as such. The capacitor is marked as such. The diode is replaced by its equivalent circuit. As you can see, it is replaced by a switch, which is actually the representative of an ideal diode, and a voltage Vk in the direction as shown. Here it is minus and here it is plus. Then of course there is the applied bias voltage. In this case, the bias voltage is written as, or it is designated as, V1. And you can see that V1 is a positive voltage here. V1 is not necessarily positive. It can be positive or negative. But for our case, we will assume that V1 is positive. And in the end equation, if V1 turns out to be negative, you can just substitute a negative voltage. That's all. So yeah, this is it. This is your load resistance, the capacitor as such. The voltage across the capacitor is marked as VC. As the input voltage changes, capacitor voltage will also change. That's why I have written VC as small letter V, meaning it is AC voltage. It is not fixed. VK and V1 are fixed voltage. That's why I have written it as capital VK, capital V1, meaning it is DC voltages. These are DC voltages. Of course, you have your V out plus minus in this direction. This is the equivalent circuit. Okay. Now, when is the diode forward biased? The diode is forward biased when the voltage at this point, okay, is less than the voltage at this point. Okay. What is the voltage at the lower point? The voltage at the lower point is V1 minus Vk. As you can see, it is V1 minus Vk. So the voltage Vn here, okay, should be less than V1 minus Vk. So let me write it like this. What is Vn? Vn is Vin itself. Since the capacitor has not charged yet, Vin completely reaches this point. That is Vin or is equal to Vn is less than V1 minus Vk, as you can see in the figure. Vin is equal to Vn. Let me write it as Vin itself so that the condition is more clear. This is the condition. Okay. During this condition, the diode is forward biased. When the diode is forward biased, my circuit will look like what? Can I draw the circuit once again? When the diode is forward biased, the capacitor, the diode is a closed switch, and then you have your Vk like this, and then the applied bias voltage. Like I said, the applied bias voltage V1 is positive here. It is not necessarily positive, but in our case I have shown it as positive. Applied voltage Vn is shown here, and then there is the output. The load resistance need not be shown, may or may not be shown. It does not come in our working. We are interested in the voltage across the load resistance, so I have marked only V out. Here you have the diode which is forward bias, so it is a closed switch. Now let us see what happens during this. the diode is forward biased. If the diode is forward biased, current will flow in this loop. In what direction will the current flow? Since Vin is less than V1 minus Vk, it is possibly in the negative half cycle. If it is in the negative half cycle, the loop equation will loop can be marked like this. You can mark it the other way around also. You will get the same equation, albeit it will be negative of what I'm writing. That's all. So taking it in this direction, it is V in is minus plus in this direction in rise in voltage. So it is V in itself. As I come down, it goes like this. The loop goes like this. Okay, right? Loop goes like this, right? So it is plus V1 minus Vk, okay, and then it goes like this, okay. As you can see, this is plus and this is minus, and therefore it is drop in voltage. So I'll mark it as minus Vc equal to 0, and that's it. What do I want from this? I want an equation for Vc. Vc is equal to V in plus V1 minus Vk. This is a very important point uh, in our work, in our functioning, because you see, you want the voltage across the capacitor, and the voltage across the capacitor, you have obtained an expression for this. What is the voltage across the capacitor at the end of this forward bias, or at the end of the half cycle? That is, what is the maximum value of Vc? That will be left hand side maximum is equal to right hand side maximum. So right hand side maximum is V in max plus maximum value of V1 minus Vk is itself, since it is constant. Okay. What is the value of V in max? V in max is Vp, let's say, plus V1 minus Vk remains as such. And Vc max, let me call it as capital Vc. This is the first equation of importance in our working. Got it. The second thing we will do is, we have done the case where Vin is less than V1 minus Vk here. The next thing we will do is we consider the case where Vin is greater than V1 minus Vk. Let's do that. Let's draw the consider Vin greater than V1 minus Vk. Consider the circuit once again. When you consider the circuit once again, you have Vin here, and here the capacitance value can be written as this. Okay. What is the polarity of the capacitance? You have minus here and plus here. Okay. So let me mark it as a constant voltage, because V1 minus Vk, Vp plus V1 minus Vk is a constant voltage. So I will mark the polarity as we have found out in the previous case, minus here and plus here. Since it is constant, I have marked it as a DC source, minus here, plus here, and the DC source value is equal to Vp plus V1 minus Vk. Okay. And then of course you have the diode equivalent circuit and the bias voltage V1, Vk and V1. Okay. This is V out plus minus V out. Okay. What happens when Vin is greater than V1 minus Vk? Okay. Vin is greater than V1 minus Vk. Let's see what happens to the diode. As you can see, the diode direction is like this. The ideal diode will be directed like this. What is the voltage at this point and what is the voltage at this point? Let me draw the diode once again here. Okay. Let me draw it as an ideal diode, or the switch. Instead of the switch, I am drawing the ideal diode. Ideal diode is just a switch. Okay. What is at this end of the switch and what is in this end of the switch? That is Vn and Vp. No, so Vp meaning the voltage at P. Okay, let's not confuse it with our peak voltage. What is the voltage at the P side of the diode? That is here. It is V1 minus Vk. Is that right? V1 minus Vk. What is the voltage at N side of the diode at this point? At this point, it is equal to, let me say that it is a positive half cycle. Since Vn is greater than V1 minus Vk, let's say that it is plus minus symbol. So it will be Vn plus, yes, Vp plus V1 minus Vk. What do you think about this voltage? This is definitely a voltage that is greater than V1 minus Vk. This voltage is definitely greater than V1 minus Vk. If it is greater than V1 minus Vk, then the voltage at N is greater and the voltage at N is less, meaning the diode is reverse biased. Do you get that? Now that we understand the diode is reverse biased, let us write the loop equation as always. The loop equation I'm going to take in this direction as I have shown here. Let's write it. So as you go in this direction, V in is positive, V in, then as you go here, it is plus Vp plus V1 minus Vk. As you can see, the voltage across the capacitor is positive. And as you complete the loop, the last one is V out in this direction plus to minus. So it is minus V out. Nothing else, therefore equal to 0. What I need from this loop equation is an equation to obtain V out. So let me isolate V out. V out is equal to V in plus Vp plus V1 minus Vk. V in plus Vp plus V1 minus Vk. This is the equation that you get for V in greater than V1 minus Vk. Now, if I take V in less than V1 minus Vk again, will I go back to this condition wherein the capacitor was charging? Yes or no? Let us see what happens. Only if I get the other condition once more, that is V in less than V1 minus Vk condition once more, can I generalize it? So let me take it again. The third case is V in less than V1 minus Vk. This one I can generalize for V in greater than V1 minus Vk, and this I am going to generalize for V in less than V1 minus Vk. To do that, let me draw the circuit once more. V in less than V1 minus Vk. The circuit looks like this. Once again, there is no path for discharge for the capacitor, so I will keep the capacitor like this. The switch, let us see whether it is open or closed. Vk direction goes like this. V1 is like this. As you can see, this is V in, and finally you have V out here plus minus. Here it is minus plus. And the voltage across the capacitor is Vp plus V1 minus Vk. This is V out. The first step is to determine whether the diode that you see here, the diode is reverse biased or forward biased. Let me see. Diode has a voltage at this end equal to, since Vin is less than V1 minus Vk, let me assume that the polarity is like this. Minus Vin, okay, what is the voltage here at this point? At this point it is, as you can see in the direction of the arrow that I have shown, it is minus Vin plus Vp plus V1 minus Vk. Okay, and at this end of the diode, that is this end, as you can see, it is V1 minus Vk. Which one will be great? Voltage at A or voltage at B? Voltage at A is equal to voltage at B plus Vp minus Vn plus Vp minus Vn. This is a positive value for sure because Vp will always be greater than Vn. Therefore, Vp minus Vn is always a positive value. In short, V1 minus Vk plus a positive value. That is the voltage here. And here it is V1 minus Vk. Definitely, the voltage at this point is greater than the voltage at this point. Voltage at N is greater than the voltage at P. Therefore, the diode remains reverse biased. Can you see that? Now that we understand the diode is reverse biased, let's write the loop equation once more. You can take the loop in any direction, of course. I'm going to take it in this direction, or you could take it in this direction. Okay, let me take it in this direction because I always like to start with the positive of the input. Input current always flows out from the positive of the input. That's why I'm taking it in this direction, but it does not matter really. So when I take it in this direction, this is the direction. Minus plus means rise in voltage. Therefore, the loop equation becomes loop equation becomes V in loop equation V in, this is plus V out. As you go here, it is minus voltage across the capacitor, that is Vp plus V1 minus Vk equal to 0. Let's isolate the value of V out equal to, V out is equal to minus V in plus Vp plus V1 minus Vk. This is the equation that you get. Combining the equations 1 and 2, you can generalize the output equation for clamper, positive bias. Let's now combine these two equations for a general equation. Okay, general equation for biased positive clamper is combining 1 and 2. Okay, I can write V out equal to Vn plus Vp plus V1 minus Vk for Vn here. Condition is greater than V1 minus Vk. And what is the second equation? V out is equal to minus Vn plus Vp plus V1 minus Vk again for what is the second condition? Vn less than V1 minus Vk. I can combine these two and generalize it as Vn, which can be positive or negative based on where it lies, plus Vp plus V1 minus Vk. So let me generalize this for all Vn. That means it could be positive in this case and negative in this case. Either way, the equation is same. The only change is in Vn being positive or negative. This is the general equation. Based on this, let us draw the waveform. Okay, input and output waveforms. Let's do that. General equation is V out is equal to Vn plus Vp plus V1 minus Vk for all values of Vn, meaning it can be greater than V1 minus Vk or less than V1 minus Vk. Based on this, like we said earlier, we're going to draw the waveform. In order to obtain or plot the output waveform, I have already drawn the input waveform. As you can see, the sinusoidal waveform is drawn. Vp is the maximum and y times Vp is the negative maximum. I have marked the key points Vn equal to 0, Vn equal to Vp, again 0, minus Vp and again 0. At these points, what is the corresponding value of output? If I can plot that, I will get the output waveform. Because you see it retains the shape. The sinusoidal shape is retained. It is just a matter of shift. So in order to get the shift, I just need to get some key points and I can understand how to draw the output waveform. First, let us substitute Vn equal to, what is the first key point? Vn equal to 0. Vn equal to 0. When Vn equal to 0, what is the value of V out? V out is equal to, let us substitute here. V out is equal to, substitute here, 0 plus Vp plus V1 minus Vk. That is equal to Vp plus V1 minus Vk. This is the output voltage for Vn equal to 0. When Vn equal to 0, the level here is Vp plus V1 minus Vk. Done. Next key point here is Vp. When Vn is equal to Vp, fixed voltage Vp. At that time, V out is equal to, substitute, Vn is equal to Vp plus V1 minus Vk. I am substituting it in the equation number 4. Okay, equation number 4. I got this. That is equal to 2Vp plus V1 minus Vk. So at this point, Vp, what I get is, let me see the corresponding point here. This is the line for Vp. When Vn is equal to Vp, what is the value here? It is 2Vp plus V1 minus Vk. Okay. So my waveform will look like this. The shape is retained like I said. So my peak here is, this is the peak. Okay. This is the peak. Again I have Vn equal to 0 here. At Vn equal to 0, we have already calculated that V out is equal to Vp plus V1 minus Vk. That is this line. So corresponding to this, we have here Vp plus V1 minus Vk. Next one we do not have in hand. We have to calculate when Vn is equal to minus Vp. Vn is equal to minus Vp. What is the corresponding value of output? Let us plot that. V out is equal to, substitute in the equation, it becomes minus Vp, substitute instead of Vn, minus Vp plus Vp plus V1 minus Vk. That is equal to 0 plus Vp plus, 0 plus V1 minus Vk. That is equal to V1 minus Vk. That is a value less than this. So let me mark it here somewhere. It would be V1 minus Vk. This point. Okay. Once again, we bring it here. When Vin is equal to minus Vp, Vout is equal to V1 minus Vp. Bring it here. Vin is equal, next Vin equal to 0. Again Vin equal to 0. What is Vout? Vp plus V1 minus Vk. That is this line. Okay. So you have like this. Okay, my shape, the shape of my waveform is not really very nice. It doesn't look exactly like the input waveform, but it is supposed to. Yeah, more or less. This is how you get the output waveform. The points are marked as I have marked it here. V1 minus Vk, Vp plus V1 minus Vk, 2 Vp plus V1 minus Vk. These are the points. Positive maximum is this, middle point is this, and this is the negative maximum. This is the output waveform for positive biased clamper with practical diode. The reason I have taken this up for revision is when I write the general equation Vout is equal to Vin plus Vp plus V1 minus Vk for all Vin, I can actually, from this I can actually obtain, this is, what was this? Positive biased with practical diode. Okay. Suppose I want the equation, output equation for positive biased with not practical diode, ideal diode. So in case of practical diode, we have a voltage of Vk. In case of ideal diode, we do not have this. Therefore, my Vout becomes equal to Vin plus Vp plus V1 minus, there is no Vk in case of ideal diode. So I'll write that as 0. Therefore, this equation is the equation for positive biased clamper. Okay, you got the idea? From this equation, for positive biased practical diode equation, I can obtain both the other equations also. Therefore, Vk is equal to 0 in case of ideal diode. Here the ideal diode case is taken. Positive biased clamper with ideal diode. In case of ideal diode, Vk becomes 0. Therefore, this is equal to Vin plus Vp plus V1. Easy, isn't it? For all Vin. This is this case. Okay. Can we do once more? One more. Positive, no bias. And it is not practical. That means ideal diode. Not practical diode, ideal diode. What about not biased, meaning there is no V1 voltage there. That means V1 equal to 0. Positive clamper with ideal diode. Then the output would be equal to Vin plus, once again you substitute here. This is the general equation. Vin plus Vp will definitely be there, plus V1. V1 is not there. We are talking about ideal diode, so Vk is not there. I can write that also as 0 for all Vin. This becomes equal to Vin plus Vp. Okay. This is the equation for positive diode. I'm sorry, positive clamper with ideal diode. I hope you understood the idea here. You can derive all the other equations from positive biased practical diode clamper. Positive biased clamper with practical diode. Okay. I hope that is clear. Let me tell you one more point. We have always assumed that V1 is a positive value in all this case. In other words, we have been discussing the clamper, positive clamper. That means the output waveform is clamped in the positive direction. Positive clamper, biased positive clamper, isn't it? When I kept saying bias, I was talking about V1, and V1 was expected to be a positive voltage. So instead of having a positive voltage V1, suppose I have a negative voltage V1. what will the name of the clamper be? It will not just be biased positive clamper. The clamper name would be, they would be asking you for a positive clamper with negative bias. Negative bias. What does this mean? This means that V1 is negative. Okay. If it is with positive bias, V1 is positive. That's how you differentiate the circuit based on the title or based on the name. I hope that is okay. Now that we have understood positive clamper with the positive bias using practical diode, let's do a negative clamper with positive bias using practical diode. This will be the circuit and the equivalent circuit would look like this. This is V in, this will be the capacitor, and this is VK, this is V1, or let us call it V2. Either way it's fine. Okay. It's a positive bias. The bias voltage is positive with respect to the output. Let's start. First case, we always take diode is forward biased. Let's do the same drill. Diode is forward biased. When is the diode forward biased? Diode is forward biased when the voltage here is greater than the voltage here. What is the voltage at P? The voltage at P is equal to V in. It should be greater than the voltage at the N of diode. What is the voltage at N? V1 plus Vk. Okay. So V in is greater than V1 plus Vk. At this time, diode is forward biased, and as you can see, since it is greater than V1 plus Vk, let's assume that this is the positive half cycle. The polarity will be as shown, plus here and minus here. Therefore, the capacitor will be plus minus like this. Let's write the equation. Next step is loop equation. Loop equation becomes, in the direction of the loop, V in, rise in voltage, fall in voltage, minus Vc, and then drop, minus V1 minus Vk, okay, is equal to 0. Or what we need is Vc, or the capacitor voltage. So Vc is equal to Vin minus V1 minus Vk, minus of V1 plus Vk. Can I write it like that? This is minus of V1 plus Vk. That's what we did. What is the maximum value of Vc? Capital Vc is equal to, what is the maximum value of V in Vp, say, minus V1 plus Vk, which is equal to constant. This is the first equation. From this first equation, we have obtained the voltage across the capacitor, and this voltage is going to be fixed. Let's draw the circuit right now. It looks like this. So for the second case, our starting circuit will look like this. Vp plus minus V1 plus Vk. Look at the polarity. Left hand side positive. Therefore, the voltage source looks like this. Okay. And this is your Vn. Then you have the diode here. The diode equivalent circuit looks like this. Vk, V1. This is V out, positive, negative. When is the diode forward biased? Once again, this is P and this is N. Voltage at P should be greater than voltage at N. What is the condition here? Right now it is, this is Vc. Okay, Vc is equal to Vp minus V1 plus Vk. Let me look at the diode, state of the diode here. Let me redraw the switch or ideal diode like this. Voltage here is, as you can see here, it is, we are considering the case where Vin is less than, we are considering the case where Vin is less than V1 plus Vk, less than or equal to V1 plus Vk. So, less than, let me assume that the polarity is like this, becomes minus Vin or minus Vc. Vc is Vp minus V1 plus Vk. Okay. What is the voltage at N? It is V1 plus Vk. Okay. Let me rewrite this, Vn minus Vp plus V1 plus Vk. This is Vn minus Vp plus V1 plus Vk. Okay. Now if I assume that this point is A and this point is B, okay, the voltage at this point is A and this is Va and this voltage at this point is Vb, which is greater? Definitely voltage at Vb is greater than Va, because you see voltage at B or Vb is equal to a quantity V1 plus Vk, and voltage at Va is a quantity V1 plus Vk minus Vn minus Vp, which is definitely a lesser value. Therefore Vb is greater than Va, which means the diode is reverse biased. This is what we were expecting and hoping for. Yes, it is reverse biased. Now the diode is reverse biased, meaning the switch is open. If the switch is open, we will not consider this arm at all. Okay. We will not consider this arm when we write the loop equation. Let's do that. Write the loop equation. Let us not consider this arm because it is open circuit. Okay. Yeah. This is VC. Let's take the loop equation. I like to write the loop equation from the positive direction. So I've marked it like this, in this direction. Okay. So V in, this goes from minus to plus. The direction of the loop I have taken is going from minus to plus like this. So plus V out, and from here it goes in this direction. Plus Vc equal to 0. I need the equation for V out. So V out is equal to minus V in minus Vc. What is the equation for Vc? Minus Vc becomes Vp minus V1 plus Vk, and we are done. This is the equation for V out. Equation number 2. Let's go for the third case. Third case, once again we are going to consider V in greater than, because initially when V in was greater than V1 plus Vk, diode was forward biased. Now the circuit looks like this, that is Vn is applied, Vc is obtained like this as see shown. Now what we have to find out is whether the diode is forward biased or reverse biased. Diode has P here and N here. Let me call this as voltage Va and this is voltage Vb. Va, as shown in the polarity here, Va is equal to, as you see here, Va comes here, Va is equal to Vn minus Vc. What is the value of Vc? I get it from equation 1. What did I get for Vc? Vp minus V1 plus Vk. Let's substitute that. Vp minus V1 plus Vk. Got that. That is equal to Vn minus Vp plus V1 plus Vk. What is Vb equal to? Vb equal to, as you can see here, this is Vb. Vb equal to V1 plus Vk. Straightforward. Which one is greater? Va is equal to, what is Va equal to? Vn minus Vp plus V1 plus Vk. What is Vb? V1 plus Vk. Which one is greater? Which one is less? Obviously, V1 plus Vk will be greater. You know why? Because this is a negative quantity. How do I know this is a negative quantity? This is equal to V1 plus Vk plus a certain quantity Vn minus Vp. Is Vn minus Vp positive or negative? The magnitude of Vn will always be less than magnitude of Vp, because Vp is the maximum value of Vn. Vp is the maximum value of Vn. So magnitude of Vn will always be less than magnitude of Vp. Therefore, when I say Vn minus Vp, this is definitely a negative value. Okay, is that okay? This is a negative value. So this is a negative value plus V1 plus Vk. Let me call it x. This is x. This is x and this is x plus a negative value. Therefore, this will be less than Vb. Va is less than Vb. This is our conclusion. If Va is less than Vb, this is less and this is greater, then this becomes reverse biased. Henceforth, the diode is reverse biased, just as in the previous condition. Henceforth, for all conditions of Vn, diode remains reverse biased. Now let's write the loop equation in this direction. As you see, Vn minus plus is rise in voltage. Let me write it as Vn itself. Fall in voltage Vc, and fall in voltage V out minus V out equal to 0. I need an equation for V out once again. V out is equal to Vn minus Vc. What is the substitution for Vc? Minus Vp minus V1 plus Vk. Okay. This is equation number 3. I've got two equations for output. Output equation I have equation number 2 and equation number 3. Combining these two, I have this and this. So combining these two, I can generalize it. V out is equal to Vn minus the capacitor voltage in both cases. But here Vn is negative and here Vn is positive. That is the only difference between these two. Now let's write the generalized equation for V out. Okay. Therefore, general equation becomes V out is equal to V in minus Vc, that is Vp minus V1 plus Vk. This is Vc for all Vn. Vn can be positive, Vn can be negative. This is the general equation for output voltage of a negative clamper with positive bias with practical diode. ഇനി നമുക്ക് waveform വരയ്ക്കാം. In order to draw the output waveform, I have written the output equation. That is the general expression I have written here. This is the expression. And from this expression, I see that V out is equal to Vn minus Vp plus V1 minus Vk for all Vn. Let's do this. Let us start just as we did for positive clamper. Start with the first value of Vn. First value of Vn in the Vn equal to 0. When Vn is equal to 0, what is V out equal to? 0 minus, substitute in this equation, 0 minus Vp plus V1 minus Vk. That is equal to minus of Vp plus V1 minus Vk. Okay. Let me assume that this is somewhere here. Okay. So it becomes, this is minus Vp minus V1 minus Vk. This is the shift in 0 point. Next, let us consider the next point. Vn equal to peak value. Let's call this as Vp. Vn equal to Vp. Therefore, V out becomes equal to Vp minus Vp plus V1 minus Vk. That is equal to Vp minus Vp 0 minus V1 plus Vk. Okay. So corresponding to this, let me mark this point as minus V1 plus Vk. Okay. Let me take one more condition. Next condition is Vn equal to 0, which we already have here. Then you have a negative peak here, minus Vp, isn't it? Let's do that. When Vn is equal to minus Vp, Vn is equal to minus Vp, then V out is equal to minus Vp minus Vp plus V1 minus Vk. Vp plus V1 minus Vk. That is equal to minus Vp minus Vp. That makes minus 2 Vp. Minus 2 Vp minus of V1 minus Vk. What do you get here? Minus 2 Vp. I'll mark it as minus 2 Vp minus of V1 minus Vk. Okay. You have all the 3 points here. For 3 points V in 0, V in Vp and V in minus Vp, I have the corresponding output voltages here. Let's mark it now and the output voltage can be plotted. This is the output waveform that you get for negative clamper with positive bias. So that's all for clampers. Once again, to obtain the individual clampers, you can substitute in the general equation. That is, this is the general equation for biased negative clamper with practical diode. And these are the remaining cases. So that's it for negative clampers. And that's all for all the clampers. Thank you.